let's start. Thank you so much. Thank you also. It is a pleasure and actually an honor to introduce Professor Leslie Valiant. Les is, of course, extremely well known for his work in theoretical computer science, his theory of the learnable, but also holographic algorithms and the BSP model for parallel and distributed computing, later adopted by MapReduced. He received many awards. When he receives an award, the award becomes more famous. I will just mention two. He is the Turing Award recipient for 2010 and also a Fellow of the Royal Society. So today Les will talk about the combination of learning and reasoning, a theme that permeates this workshop since its beginning. And as part of his more recent work on robust logic, which is central to this community, in his own words, which I've quoted many times in my own papers, reconciling the statistical nature of learning with the logical nature of reasoning. So without further delay, Les, thank you so much for accepting Louis Lamb's and my invitation to give this talk. It's great to have you here. The floor is yours. Thank you.
Thank you very much for the invitation to this wonderful workshop and beautiful place. And thank you for the very generous introduction. So this topic I'm going to talk about, I've been working on for a long time, which is mixing learning and reasoning. And since many people in the room are doing the same thing, I think in various ways, I'll try to clarify kind of my special angle on it. So I like kind of natural phenomena in the world, and I think theories should explain phenomena, and maybe we should reproduce it with computers. So I think the phenomenon I'm interested in is cognition, human cognition, and the fact that we can reason on information which we've learned, and on the information which is presumably uncertain. And so this issue is sandwiched between, of course, two big areas, logic and learning. And the question is, what to do about it. And so basically what I'm going to describe is, on the one hand, a theory, which is a very old theory of mine, but I've not managed to free myself of it, which is a theory of this. But then the other side of the coin is to show, if you've got a theory, is to show that it explains the phenomenon. And there, I fall short. I don't know how to do it. Okay, so I need help on that. So we can have wonderful theories, but how do they correspond to the actual phenomenon? And so one thing I want to emphasize is that we're torn between logic and learning. Both are wonderful theories and work wonderfully in practice. There are theories which predict exactly what you want to do. And further, what I want to emphasize is that both have this aspect that at one point you can discard the theory. So for example, if you've got a proof, your 200-page proof, you just have to check it. You don't have to figure out where it came from. And similarly with machine learning, if you've trained some network and you think it works well for predicting pictures of elephants on the web, then it's easy to just statistically sample and verify and finished kind of thing, that the theory is almost separated from the empirical verification. But when we're trying to do something new, we have to worry both about what we're going to achieve and also how we're going to convince ourselves that we've done anything useful. Now, learning and reasoning are in fact so wonderful that there are people who deny the other. Okay, so certainly when I started in an AI conference, machine learning was, there was no statistics, it was all about logic. Whereas now, many people are so enthusiastic about machine learning that they deny reasoning. So the problem here is that we may think, in this room, we may think that these people are crazy, but it's difficult to actually refute either of them totally, okay? And of course, one issue is that there are some trade-offs, so probably if you get more data for learning, then maybe you have to do less reasoning, okay? So it's a non-trivial thing how to resolve this. And so one question which we all come across is that to convince oneself that a theory satisfies a phenomenon, you have to do some empirical work. But no empirical work is the last word, because if you build a system which mixes learning and reasoning and both seem necessary, maybe next year the learning methods will be much better, and you won't have what you've shown doesn't apply anymore. So it's a moving target. So how to convince oneself that one is doing something in this area? The approach I've taken is that one should have a reasoning system which reasons on learned knowledge. So whatever your theory is, you should see how it works in practice. And the question is whether it can work better than just a pure end-to-end machine learning system. Okay, so if you think that reasoning is helpful on top of learning, then show an example. Okay, and then okay, so issues here, because this is a partly theoretical talk. Okay, is we have to define what reasoning is, and we also have to define what outperform is, which is roughly what this slide says. But just as a forward pointer, so this talk is basically theoretical, but if you want to take a very concrete, practical approach to this, then the practical aspect of the talk, in fact, is very easy to explain now, which it wasn't a year ago. So it's very close to the question of if you really wanted to make a large language model like ChatGPT more reliable for learning, for reasoning, what would you actually do? Okay, so this is, you can take it as a proposal for what you do to language models to make the reasoning better. Okay, so again, slightly on the philosophical side. So I like looking at phenomena, and so with machine learning, supervised learning, we all know what supervised learning is, and the varieties like self-supervised learning, where the supervisor is part of the input, that's regarded as the same thing. And then we know that the influential algorithms, the influential data sets, and we have to compute it on some machine. But so what I've been interested in is defining more precisely what the phenomenon is we're doing. So my work on packed learning basically was a definition of what efficient generalization is. So if you train some program to generalize to future examples, what exactly does that mean? And so just to a very quick historical recap of that. So in the early 80s, when I was looking at this, so if you look at a class of expressions, these are 3 CNF Boolean expressions. So you've got A, B, C are variables, and a prime means negation. And we know that, so are these simple or complicated, these expressions? Well, in some sense, they're simple. In another sense, they're complicated because Stephen Cook showed that if someone gives you an expression like this, you can't tell whether it's equivalent to just the 0 expression. Maybe there's no assignment of zeros and ones to the A's, B's, and C's, which make it true. Okay, so in some sense, these expressions are complicated. On the other hand, this one could show to be efficiently learnable in a rigorous sense. And of course, there's no contradiction here because the point of the learning model is that there's a distribution of the possible inputs. So if you've got n Boolean variables, you've got 2 to the n assignments. For the learning problem, each has some probability. So if this formula is false, except very rarely, then the learner doesn't need to find out the few exceptions, because for almost all inputs, this formula will say no. Okay, so learning is very different from computation, some things which certainly very different from testing satisfiability. Okay, so anyway, so that's one aspect of a model of learning. As I said, so this packed learning, supervised learning is something very simple about it in that, it's very easy to recognize whether you're succeeding as a pragmatic, as a empirically. So I think this Irvine repository of machine learning data sets was very influential in having people experiment with lots of learning algorithms. Okay, so going back, so this packed learning was a formulation of supervised learning, which formulated as efficient generalization. Okay, and the main point I want to make now is that this is all the definition does. It talks about generalization. So now, of course, many people complain that practical learning methods don't do many things like explainability, spurious correlations, adversarial examples, lifelong learning, which we would think that supervised learning of a human can somehow do. Okay, but of course, one shouldn't complain because certainly the theoretical model doesn't promise any of these, and all these algorithms we use for learning have been trained and selected very carefully just to do efficient generalization. And for all the other things, you have to do something different. They're not promised by the model. They're not promised by the empirical experiments which led us to where we are. So I'm just making the philosophical point that a theoretical model can tell you, what you're doing, but equally importantly, it tells you what you're not doing. Okay, so if, for example, ChatGPT is a generalizer for the next token in text, that's what it's trained to do, then why do people, discuss it as if it was doing much more magical things? It's absurd. Okay, so we should recognize what it's doing. Okay, so what I want to do now is something analogous, but with reasoning and learned knowledge. And I do have this logical system, this system called robust logic, which is like a formal model. And I want to describe that, and also, I'll mix up my efforts at understanding what this is, a bit of the theoretical setup, and also experimentally what it amounts to. Okay, so most basically, the competition here is between having a single supervised learning box, end-to-end learning, versus something better. And my robust logic amounts to having many of these supervised learning boxes, which may be trained separately or together. But the point is that the inputs and the outputs of those boxes are connected, and there's a principled way of chaining the conclusions of the boxes. Okay, so that's the main thing, that reasoning will consist of chaining conclusions of the boxes, and there will be some reasons why you should believe the chaining. Okay, so packed learning is a formulation of efficient generalization. Discusses that that if you put more and more effort in, you get more and more accurate. So this robust logic takes all that over, but it's more flexible because it combines reasoning as well. And in effect, it has a principled way of chaining different boxes, and the error of the chaining is similarly controlled in the same way as it is for learning. So the more and more effort you put into the learning, then hopefully the more and more accurate your reasoning will be. Okay. Okay. So So now let's go back to this philosophical question whether we can solve it by discussion. So is end-to-end supervised learning enough, or do we need this reasoning? So the problem which with the student Loisios Michael some years ago we decided to test this on is the word completion problem. It's essentially what's called large language models now. And so as an illustration, what I like doing is it's basically I give you a sentence, I delete a word. The question is, can your computer system substitute the word? Okay, and doing this for headlines in websites or newspapers is quite interesting because headlines tend to be succinct. Okay, So, okay, so these I took in, I spent 3 minutes picking out these 3 headlines from La Stampa before I left, okay? So this is a generally good AI problem from my point of view, because there's a ground truth. Okay, for example, one headline said, Cassius, the world's largest living crocodile, turns. Okay, so this newspaper did have an answer to that, so there's a ground truth. And the question is, can you, as a human, predict it? Can your computer predict it? Presumably from learning and reasoning. And where we're going is that you see how well a pure learning system can do, a bit like ChatGPT, and see whether you can do better if you do some extra reasoning, okay? Okay, so this one I won't, okay, so here ChatGPT said 120, and then I asked Google, and Google said that there are 420,000 web pages which have Cassius crocodile 120. So apparently this crocodile has been turning 120 for many years, and there are lots of headlines in the media about this. Okay, so this is a trivial problem. You don't need reasoning. You can look this up in 1,000 pages. So if you're, so here just end-to-end learning, solve it. Okay, so many problems are like this. Okay, so let's try a second one. Oops, okay. Okay, so Paris says goodbye to. Can anyone guess? Sorry? Well, sorry? Oh, okay, that's a possibility. Okay. Well, ChatGPT said Eiffel Tower. Okay. But the newspaper said skyscrapers. Okay, so some regulation. Okay. Okay, and the last one. So again, I don't want to be controversial, but again, this was in the newspaper. Refuses to fly flags at half-mast for Berlusconi. The rector of Siena risks. Okay. So the ChatGPT said backlash and controversy. Can anyone guess what the newspaper said? Okay, no, it's even worse. After 3 months in prison. Okay. So so this is now serious. Okay, because I'm not sure whether this is accurate, but so people do have to make decisions, and people do have to reason. And certainly this person had a reasoning problem, and probably he shouldn't have trusted ChatGPT to make his important decision. Okay, so so having reasoning systems which you can trust on real-world data is an important question. Okay, so anyway, so that's just trying to explain that. So some of these tasks, one would think, you can't just solve by taking lots of examples from the web. So the fact that we think the Eiffel Tower is an unlikely answer is because we use other information that it's unlikely that's what Paris wants to get rid of. Okay, so so the experiment we did was similar to this. This is Loisius Michael. So at that time, this was obviously a Stone Age experiment. So at that time, the Wall Street Journal was a well-known data set for text. We did some very simple NLP things, mechanical parser for subject-object, a bit of a knowledge graph that was WordNet. But actually, we were just predicting from single sentences. It was very, very primitive. But our goal was, we weren't, so our goal was to learn rules about the world and then use these rules to predict the next word. So predicting the next word was this NLP task, which maybe we can do better if we can reason them. But when you reason, you need to, you believe that there's some rules about the world which go beyond just the linguistic statement. Okay, so we try to learn these rules that express word knowledge. Then we chain these together to depth 1 or 2, and things go wrong if you chain these things too much. And then the question was, could we do better than pure baseline learning? So how to do this really honestly? Who knows? Maybe you should make sure that you put the same number of dollars or cycles into the pure learning versus the learning plus something else. It's all kinds of trade-offs. So this is what we did. And so we use this learning thing, again, to predict the next word from this Wall Street Journal. So this Wall Street Journal text, Wall Street Journal is about business. It's got very restricted kind of information in it. And so we picked out about 250 words, which occurred frequently enough in a small database that, there was some information. And so in this slightly confusing graph, so the words are listed from 0 to 250, from left to right. And the words on which we did best with our method are to the right. Okay, so the words are ordered to favor us on the right. And the only thing you should look at is this red line E at the top and the blue line D. And the difference between the red line and the blue line is how much better we did with our reasoning method, which I haven't described yet to you, over a vanilla learning method, which also I haven't described. Okay. But certainly one feature is that if you go to the left, you find that, in fact, the blue line, which is the vanilla learning, is better than the reasoning. Okay, so there are these trade-offs that if you try doing something complicated, if you don't have enough data, it's very noisy, and you do worse than if you do. Okay. So in fact, I think there's some profound implication here is that if you, in a big machine learning effort like ChatGPT, is very hard to give up because just the enormous data set on which everything is trained on, it's very good at something. So competing with that is quite difficult because on some things you'll do worse if you do something else. But obviously, for this experiment, for some words which we really got some information about the world, about these concepts, which were better than our machine learning algorithm. So before I describe some details, so just in rough terms, so in the PAC model, basically you're not building a model of the world. Okay, so this applies to cases where the world is just too complicated to build a model of the world in the traditional sense. So this works when there are like rules of thumb which work most of the time. Okay, and so I think this is how cognition works. So there will be multiple objects and relations in the sense of predicate calculus, and so it's very important that it supports partial information because when we think in each instance we're given a very small amount of information to think about, and most features are unspecified. So this is very different from standard machine learning, where if you're looking at the pictures on the web, all the pictures are there, and that's what you're learning from. So here I'm using learning algorithm as a black box. So maybe I should say at this point that as far as language, so when I mean reasoning and this cognition, it's clearly I'm talking about symbolic things. Okay, there's no question of that. As far as the learning, actually I'm neutral on how you learn, but most people learn with, most learning algorithms do use continuous variables. So it is a neural. If you use a neurally inspired learning algorithm, then you're doing neurally inspired symbolic computation. But as far as this theory, I don't care how you learn. Don't care what's inside the learning box. And then what you go to all this trouble for the one important thing, which is to be able to chain the rules soundly. Okay, whatever that means. Okay, so now I'll just describe in rough terms what this model is. So the model is based on an attention mechanism in the sense of cognitive science. So the idea is that when you wake up in the morning, you've got a set of tokens which are undifferentiated, and when you think of something, then you attach predicates and relations to these tokens. So this would represent the fact that there's a dog, you're thinking about a dog, and the dog likes something. Okay? And it may be that you know that dogs like bones. And it may be your conclusion that therefore what the dog likes is a bone. Now a logical rule would be something like this. So if there's a dog and the dog likes something, then there's something else as a bone. So in robust logic, these things we can't learn. So classifiers are not implications, they're if and only if conditions. Okay, so if you predict something is an elephant, you want it to be an elephant, and if it's not an elephant, you want to predict it's not an elephant. It's not an implication is the one-way thing. So, so basically in the robust logic framework, where you do everything by machine learning, you need a classifier which says bone or not bone under all, not all conditions, but with high probability on your input space. Okay. But the robust logic rule will be an expression from a learnable class, which you may as well say it could be a deep neural net. Okay, it'll be some machine learning classifier you've learned, which can predict bone. Okay, and we're going to use these things for training. So the left-hand side is a learned classifier. The right-hand side is some predicate which you've identified as of interest to you, and of course the bone could be an input, a predicate for input to another classifier, so you can chain these things together. Okay, so so we're going to learn logical rules become classifiers with simple right-hand sides. So we learn equalities. We learn approximate equivalences, to be exact. Within the, as I'll show, so within this, when I say expression from learnable class, the inputs will be Booleanized, but I can have compound variables. And for example, I could have inputs which do represent the there exists. Okay, so there exists means that within your mind's eye, there exists one token with the required properties. Okay, so so depending on how you do it, so this whole left-hand side could be a single Boolean variable, which you get by combinatorially combining some base set of variables. Of course, if you do this, your number of variables does blow up, so you have to be careful. So, but there's some possibility for using local quantifiers. Okay. Okay. So the rules are learned, and so you know where they're learned from, and the idea here is that this creature sees the world entirely through its mind's eye, and for whatever reason, it's experienced a certain set of configurations. Maybe 27 times it's seen that examples of dogs that like bones, and because of that, it's learned this rule. Okay, so as you can think, it's an interface between the world and this formalism is nothing other than this set of okay. So a scene is an example of a set of tokens with these predicates on them. Okay, so a particular scene would say there's a dog which likes a bone. Okay, and then in the experience of this creature, it will have seen lots of these scenes, and it'll learn what it can learn, what's learnable. It'll learn good generalizations. Maybe the world is so complicated it can't learn anything, but it'll figure that out, because if it can't learn, like if you do machine learning, maybe you fail because the data is too complicated for your learning algorithm. Okay, so the D, the natural distribution from which you learn and on which you have to perform well, are the examples in your mind's eye. And then there's some complications, because I do want them to be also partially specified. So this dog may have 1,000 other features, but no one tells us the features of this dog. So how do we operate in this world where the examples are, partially specified? Okay, so that's a problem, but there's a reasonable solution to that, which is that you imagine a very large set of variables, which include a whole space of possible variables, and then a single instance will, if in a single instance, most of the variables won't be specified. They're kind of hidden. Okay. Okay, so that gives rise to complications, but basically what it amounts to saying is that if you're going to learn about dogs and you learn some generalization about dogs where very little else is specified about the dog, the generalization had better be correct, independent of the other features. Okay, so anyway, okay, so that's okay. So I'm just listing some features. Fifth thing is that we're going to learn these various rules, which we learned like in the machine learning sense, and there's no consistency enforced. So we learn about elephants, we learn about this, we learn about that, and sometimes maybe when we chain together these rules, we'll get a contradiction. We'll figure out that the rules are in conflict. Well, there's no chance of anyone enforcing consistency. This is a different game. This is a probabilistic game. It's not a deterministic logic. But in practice, the solution is that if you find that there's some conflict, which occurs often enough, then you'll kind of learn your way out of it. So if there's a conflict, then some of your rules must be inaccurate. So if you take more examples, then you'll, So for example, if this old Nixon diamond problem, so if Richard Nixon comes up often enough and you can't decide whether he's a pacifist or not, then the rules which lead you to two different conclusions, you'll have to revise one of them in the light of more knowledge about Richard Nixon, maybe. Okay, so you learn your way out of inconsistencies which you don't like. Otherwise, you just live with the inconsistencies. And okay, so just the last feature I want to mention is that so basically, it's when you learn hierarchically, it's very hard to learn something on top of something else if you only half understand something. So if you go to a math class and you only half understand what a group is, it'll be rather hard to learn something which depends on the lower definition. Okay, so so for the system, it is an assumption for this to work is that the examples do come with correct labels. Of course, in a natural language input, this is taken for granted. Okay, so in a large language model, you assume that all the words are correct. Okay, and the next word and the previous word, you assume it's correct. So this is not a big ask, but it's something which one, if one goes away from this pure language models, then it's a restriction. It's just that you need the target and the variables that it depends on to be both accurately described. If things are very noisy, things are hard. Okay, so so that's roughly I've described what this robust logic is. Now let's go back to this experiment. So this experiment on the Wall Street Journal learned rules to predict the next word. Okay, so this particular rule is its equivalence, complicated left-hand side, some neural net or whatever. In this case, it's just a linear threshold function, and it predicts whether the missing word was price. Okay, so you want a predictor for whether the missing word is price, and then on the left-hand side, so I'm putting this in because most of the rules are hard to interpret, but this one you can kind of figure out. Okay, so this says basically that if something is a bargain, if there's something in the sentence which is a bargain X, and it lowers Y, then the bargains lower the price. Okay, so it's a fact about the world, which this thing managed to learn. And also, competition also, if competition lowers something, lowers the price. Okay, so this managed to figure out these rules about the world from these Wall Street Journal articles. Okay, and in this experiment, we used linear inequality. So this whole thing was done on a laptop. Okay, so so the basic robust logic formalism is described in this AIJ journal in the year 2000. Okay, so the scenes are on T objects, so these blue circles I drew. You have T of them, could be 20. Actually, things don't grow exponentially in them. Of course, there's famous psychological experiments about how many notions we can keep in our mind's eye. Yes, it's expensive to have many, but it's not exponential. So the right-hand sides are you choose. So there could be words in the dictionary, or maybe every word in the dictionary you choose, and there could be relations on two things. So as I said, the left-hand side is any learnable class you like, which you can afford to learn, depending on your computing budget. So we Booleanize all the inputs. So we need learning algorithms which are just work on Boolean inputs. And again, we can combinatorially blow up the number of variables by ANDing pairs together and having some qualification. It gets expensive if you do it in a lazy way. And the learning algorithm you pick for its good characteristics. So accuracy is one, but attribute efficiency is another. That when we blow up the number of variables, then most concepts should depend on very few of them. So attribute efficiency means that even if there are a million variables, there's the assumption that a concept depends on maybe only 5 of them. Okay, and you don't want to pay the price, too heavy price for the million. So anyway, so and so the main guarantee you get is that when you chain the rules, so when you pass the conclusion of these various learning boxes through each other, then it's sound. So this is sound in the sense of logic, except in the probabilistic weakening of it. Basically, it amounts to saying that if one of your boxes is 99% accurate, the next one is also 99% accurate. When you chain them together, the likelihood of a mistake is about 98%. Okay, so you're controlling the likelihood of error in terms of the likelihood of an error of each box. So you control the accuracy of each box just by learning. And then, because of the way you've set this up, you're also controlling, this robust logic gives you some promises that you're controlling the errors you get when you combine, when you reason. Okay. So as far as the complexity of all this, so actually the runtime you can make polynomial in almost everything. So how big are the rules? How many rules do you have? How many objects in your mind's eye? They're all polynomial dependence. So the only thing which is critical is the arity of the relations. So if you have a relation of 2 variables or 3 variables, it's exponential in the arity. So if you have, okay. But as far as describing the world in terms of relations of small arity, people generally don't complain that no one expects me to have predicates of 100 variables where this predicate depends on the 100 particular people in the room. Okay, as long as I know there's the left-hand group and the right-hand group, I can manage 2 groups, but not 100. But anyway, but that's a restriction. Okay, so just where does this bring us? So I've had this before. So I do have this formalization of what reasoning on learned information needs to be able to do to have some dependability, and I don't know how else to do anything quite like this. But as I said, the problem is how to show that this is useful. And of course, one problem is that if I'm showing it to be useful by competing against some pure learning thing, then the pure learning things are going ahead very fast. So if I'm competing against multi-million-dollar large language models, then I have to start writing my system for bigger and bigger machines and investing more and more. So that's difficult. But still, so the question is, how does one? What's this good for? So certainly one possibility is to have these large language models spend some effort on doing this internally, which means that each of the separate learning boxes will be trained for less time, they'll be less accurate, but it'll know more about the world and it can combine them in a more flexible way. So in some sense, current large language models like ChatGPT, you can think of it as a very special case of this, where you predict the next token, and then the answer you cycle back and you pick the next one and you pick the next one. So it's almost like what the large language model people call tokens, which is the next fragment of the word, becomes almost like what I call tokens, which isn't exactly the same. So basically, they have their tokens in a straight line, and whereas for my tokens, they can take arbitrary relations. Okay, so the fact that these large language models do some kind of reasoning sometimes, isn't surprising. So basically, they can do reasoning if their tokens, if their thoughts if they spit out each word as part of their reasoning. Okay, so their internal the values they give to these tokens, they speak to themselves word by word, and as long as you can chain together the reason in a straight line, then they can do it. And that's roughly what they're good at. So it's not a mystery that these large language models can sometimes do reasoning. It's not a mystery that you can encourage them to do more reasoning if you prompt them to take smaller steps. Okay, but this is still something different, and is more investment. But short of doing this, what else could this be useful for? Well, possibly more likely is testing it on a more restricted domain. So one wants a domain which is rich with knowledge, but there are kind of rules to be discovered. Okay, so what this is good at is to discover rules which you're sure there are some rules, and knowing the rules would help you reason, but it's hard to find them. You have to put a big effort into learning them from lots of data. So some micro world where people want to do better as far as reasoning, so people have mentioned some scientific applications, chemistry, I don't know. So one wants some domain in which one can demonstrate this large-scale learning and reasoning of this kind. Okay, so that's basically what I wanted to say. Okay, so I think there's a phenomenon here to address, and I'll be very interested in what other people's view is on this particular phenomenon, and certainly work is by no means finished. So, thank you.
Thank you, very insightful talk. So Rob Shapiro was your student, and under you, boosting was born. All these features are met by boosting or by other boost. Any thoughts on that? Can we think about boosting as a reasoning machine? Still, ensembles are the most deployed models.
Yeah, so don't quite. Maybe
all the features that you mentioned are met by ensembles. If you look at them one by one.
They're met by ensembles?
Right, ensemble methods. They're satisfied by ensembles.
Okay, well, I don't understand what you're saying, but maybe we should talk about it afterwards.
So could you think about boosting as a reasoning machine?
I don't. Yeah, I don't know. I'm very interested.
So I have just two quick questions. On the tractability slide, where you show the tractability of the results, so when you say the number of rules, what do you mean by number of rules? It's conjunction, like you could just conjunct multiple rules to have one rule. And what's the restriction on the language that you have? So,
well, the language of the rules is whatever learning algorithm, whatever learning algorithm you choose. So you choose a neural net of size so many, that will be one rule. So the rule sizes will be how big each of those is. Then the number of rules will be the number of learning boxes.
okay. And then the second question is, how do you, since you're dealing with some logical structure, so there is some relation, right? So if you have likes, so X1 depends on X2. Whereas in pack learning, you have a strong IID assumption, right? You cannot just sample relational to each other, right? Whereas here you have the relations. So how do you deal with that?
Well, yes, I mean that's the core of it. That I mean, you do assume that you're learning from that there's one world you're learning from, and you learn from there's a distribution of these scenes and relational things, so you have to show that the rules you learn from this one world of scenes when you chain them together has some soundness. Okay, so you have you have to thread through everything you say.
Okay.
One can't evade that. Yeah, so that's the substance. Yeah.
Thank you.
Yeah.
So actually, my question is very much on the same topic. So, so I was wondering whether the polytime complexity, whether I would need to build all the rules and learn all the rules before I can do any deduction, and if so, even if it's polytime, would then not impact? I mean, it's polynomial, but I could imagine that I would need to learn so many relations and so many predicates that in the end, that would have a big impact on the inference time and inference, while maintaining a polynomial, obviously. Any thoughts on this?
Yeah, so I mean, you have to be very careful, you know, so one is throwing around polynomials here, you have to be very careful. So certainly my then student, Logitas Michael, did an implementation of this on a laptop, very careful, very, clever things, and, managed to get useful results out of it. So, yeah, so if one implements this on a chatbot kind of scale, yeah, you have to be very clever and judicious in what you put in, yeah, because things grow up very fast. But I think there's scope for, I mean, if you want if you know what kind of areas you want the reasoning to be most accurate in, okay, then you can focus on that. Maybe you don't want reasoning on everything. So it's not the easiest road to travel, but it's a possible road.
Les, thank you for the talk. Could you just tell us a little bit more about the chaining of the learned rules? Yeah.
Well, the chaining is just that you've got these you've got a classifier, and the inputs maybe complicated little expressions in terms of the outputs of other classifiers. So it's just a flow flowing through.
So you're taking the output from those and feeding them into
Yeah.
I was wondering, a lot of people, when they talk about chaining of rules or about uncertainty, they would work with probabilistic logics. Some people also with fuzzy logics. This seems to be different. Is there any connection, any kind of reason or connection that you see?
Well, I think I think what I have in mind is a very large-scale system where we've got no hope of modeling the world probabilistically. So this the whole pack approach is minimalist in that you think that certain things you can reliably predict, most things you'll pass on. So if there are a few things in the world which you can reliably predict, and you chain those together, this is kind of the world this is about. That the world is, it's too complicated to model, I think. So probabilistic logic to me means that you assign probabilities to everything, and I don't, I think that's too hard. So this is that's too hard. This is an easier thing to do, to not assign probabilities to everything, but concentrate on what's true with high likelihood. And so my intuition about our cognition is that that's kind of how we work, that we have lots of rules of thumb, we know where to get coffee, and we know lots of things which work most of the time, but we don't work out conditional probabilities to any accuracy.
Don't the weights play a similar role as the probabilities then? I mean, you have weights, is that like probability as well, in a sense, or
well, no. I mean, in the learning boxes, you have whatever your learning method has. Okay, I don't care what's inside the learning box. But beyond that, it's kind of deterministic. I mean, it's a probabilistic claim being made. Okay, so there's a natural real-world distribution, and as impact learning is a probabilistic claim about how good this deterministic method will work in this probabilistic world. But the method isn't very probabilistic, no.
I'll jump in quickly. Can you say a few words more about the soundness result? Because I think that may be related to that question. So you have your obscured scenes, and those are atoms with truth values 1 or 0, but you don't know, right? So you don't attach 0.5 to those. And how do you get your soundness result as part of the chaining?
So so the probabilistic arguments are all kind of union bounds. Okay, so they're very rough union bounds. So they're robust in that sense. They don't depend on any assumptions. So what can I say about them? But you just show that the probability of something going wrong is small by the union bound. Okay.
Thank you, Frank.
Thank you for the talk. I want to pursue the same topic a little bit more. So I guess another way of asking Luke's question is, what would be the semantics of the numbers that you attach? So in fuzzy logic, they are degrees of membership of a fuzzy set. In probabilistic logic, we know what probabilities are. We have a formal model. So is there a way of describing what the semantics of the numbers are, apart from the function that they play in the algorithm, which you explained?
But I don't have numbers, okay? I mean, the learning, if I use a deep network for my prediction, there are numbers in there, and they mean whatever they mean in deep learning. But when I combine them, I don't have any numbers anymore. The only claim is that on this real-world distribution, claim is like impact learning on this real-world distribution, which no one describes. It'll make predictions with a small enough error. Okay, so there are no numbers in the. I mean, if you don't look inside the learning boxes, there are no numbers in the system. We ascribe numbers to our confidence in the reliability of a prediction, just in terms of our training method, how often in the training method it was accurate. Okay, so we don't have the. Okay, so that's the point. Those numbers are missing in this. We don't have those numbers. We don't estimate probabilities.
Hello. In the general context of all these questions, you assume that each rule is sound, and therefore the meaning of the rules is also sound to a degree of some error. I understand that, but isn't application of robust logic in the real world where so many things have ambiguity, how does robust logic kind of address those kind of objects in a scene which could be ambiguous or have a level of ambiguity on which a rule cannot be absolutely sound?
Well, okay, so I don't quite know by ambiguity, but so this theory, the boxes are successful learners, okay? So you've trained them so they're accurate to 99%. I mean, you may have tried, like when we trained this Wall Street Journal thing, for half the words, what we've trained is no good, so we throw those things away, okay? So So where our training succeeded, our learning method was good enough for the data, we're confident that it's going to predict with good accuracy. So, so the question is for your learning task fragment. I mean, either it's learnable by this method, either it's learnable by my learning method, or it's not. If it's ambiguous and whatever, yeah, I give up. Yeah. Yes.
So essentially, it ignores the things that are too ambiguous to fit into the robust logic.
So it ignores things which are.
I mean, in terms of your natural language, if you have a title that's ambiguous in terms of the parsing of it or the semantics of it, then because it does not fit into the model of robust logic, you've excluded it from the training of your model, the system.
Well, I'm not sure whether I've excluded the training. It's just that I've on something the learning must have failed because it still finds it ambiguous. It can't resolve between two things, so the learning has failed. And then boxes which fail, I don't use for reasoning.
Okay, great. Thank you so much. I think we need to wrap up. Let's thank the speaker again. Thank you. So now we will have 2 spotlights, and then we have a coffee break, and we come back for the third spotlight. It's a small change in the schedule, and then we will finish with the keynote by Fosca Gianotti.
So our first paper is the one from Umili, Argenziano, Barbin, and Capobianco, and it's visual reward machines. So, Elena, the stage is yours.
Okay, hi everybody. My name is Elena Umili. I'm going to present visual reward machines. So, the objective of our work is to extend the current line of linear temporal logic for non-Markovian reinforcement learning domain to non-symbolic tasks. We take inspiration from a prior work called reward machines. Reward machines have the limitation that can be applied only on symbolic state problem, and we extend it to non-symbolic tasks. In particular, we focus on states that are images. So for this reason, we call it, can you hear me? So for this reason, we call it visual reward machines. So let me give you a little bit of background. So as you probably, many of you know, reinforcement learning is that area of machine learning regarding with learning from experience. So we have an agent inside an environment. The agent can act in the environment and receive a feedback of its behavior, and it has to maximize the feedback. So this agent environment interaction is modeled as a Markov decision process that is a tuple S, A, T are gamma, where S is the state space, A is the action space, T is the transition function, R is the reward function, and gamma is the discount factor. And the term Markovian means that the state enjoys the Markovian property, so we have the future states are conditionally independent by past states given the current state. This means that the current state is enough to decide which action to take in a current moment. However, many complex tasks cannot be modeled as MDPs. And for this task, we speak about non-Markovian reinforcement learning. In these problems, we have that the transition function and or the reward function is not Markovian, so it does not depend only on the current state, but it depends on all the history of state action pairs. So let me give you an example. We designed this environment to do our experiments inspired by the Minecraft video game. So in the Minecraft video game, you have to take the pickaxe in order to take the wood, and then take the wood in order to create a table. So there is a hierarchy of items that you have to collect, we reproduce the same concept here in Little. So we have an agent that has to collect the Pikachu in order to take the gem, and has to take the gem in order to open the door and achieve the task. So given this task specification, and given that the state you receive from the environment is an image like the one you see here, the state is not Markovian, because from this image alone you cannot observe if you already collected some items in the environment or not. So the most common approach to non-Markovian reinforcement learning problems is the one based on recurrent neural networks. So we can pre-process sequences of data, of interaction data with the RNN, and run reinforcement learning algorithm on the hidden state of the RNN. However, this approach has no theoretical guarantees the hidden state of the RNN will be Markovian, even if in practice it can work. Another approach is the one based on LTL. LTL, linear temporal logic, is a modal logic extending propositional logic with temporal operators. So with these temporal operators we can express properties that must hold through time, like for example temporal constraints, specification of dynamic models, and so on. And we focus on a fragment of LTL that is LTLF, so linear temporal logic over finite traces, in which we assume the traces must have a finite length. This is not such a big limitation for many domains, and it has a nice property that an LTLF formula can be translated into an equivalent DFA. So reward machines are a DFA-based approach for non-Markovian RL problems that works like that. We have to specify the task in LTLF, then we translate it into a DFA, and we monitor the DFA state during the agent interaction with the environment, and we augment the environment state space with the state of the DFA, because we have some theoretical guarantees that this product between the state space of the automaton and the state space of the environment is Markovian. Then we can apply non-reinforcement learning algorithms on this state. This is the strength of the approach. However, to apply reward machines to a task, you have to know many things. You have to know the symbol grounding function, so a mapping between the environment states that you see and the symbols the automaton can process. And you have to know, of course, the temporal property. So coming back to the example, this task specification that is stated in natural language can be translated into three LTLF formulas, one imposing the collection of the items in the right order, one that is a safety constraint so that we have to always avoid the lava, and another one ensuring the goal. If we do an end of all these three formulas and we convert it into an automaton, we have something like that, and we can run the reward machine approach on this. So summarizing, these are the two main approaches on non-Markov reinforcement learning. The one based on RNN does not require any prior knowledge, but has no theoretical guarantees that the hidden state is Markovian, while the other one, reward machines, require too much prior knowledge. We have to know the symbol grounding function and the temporal logic specification in advance, and but it has some theoretical guarantees. So in order to combine the two, to take the strength of both, we design visual reward machines. So we define a visual reward machine like a tuple, SP, Q are Q0, delta TP, delta RP, SG, where S is the state space of the environment, P is the set is the alphabet of the automaton, so the set of symbols the automaton can possess, and Q is the automaton state space. R is a set of values, possible values for the reward. Q0 is the initial state of the automaton, and then we have the two the transition function and the reward function of the automaton that are defined as in a probabilistic way. So differently from the reward machine, we define the probability that given we are in a certain state of the automaton and we receive a certain symbol, we transit to another state, and the probability that is the transition probability, and the probability that given we are in a certain state, we receive a certain reward. Finally, we have the symbol grounding function, still defined in a probabilistic way. So the probability that a certain state represents a certain symbol, and this maintains the link between the two representations, the one used in the environment and the one used by the automaton. So if we know all the models in this definition, we can use these models to produce the next reward given a sequence of state as reward machine does, but with the difference that we can process also a sequence of state that is not symbolic, because we use the symbol grounding function to map these states to a symbolic representation. And another difference is that we can impose task specifications that are they can be also probabilistic. They are not forced to be only deterministic. So it's more general than reward machine. But the most interesting fact is that this is we define a framework to do also learning with this model, and this is the neural framework, in which we basically we implemented the three functions that we have: the symbol grounding function, the transition of the automaton, and the reward function on the automaton as parametric learnable functions. That can be learned through this framework. So we have a symbol grounding module that implements the symbol grounding function, an hidden state module H that implements the transition of the DFA, and an output module Y that implements the reward. So if you look at the framework, it resembles very closely a CNN plus combined with an RNN, with the difference that all the states of the states of the RNN are one hot, and the same for the reward, and the same for the output of the symbol grounding. So which problem we can solve with this framework? We can, in principle, learn everything that is missing in the definition. In particular, we focus on two types of problems. We focused on learning the symbol grounding function, given that we have the specification of the temporal property. This can be done by learning this framework, fixing the parameters of the DFA structure and letting learn about the parameter of the symbol grounding function, and learn to predict the sequences of reward given a sequence of states using, for example, cost entropy. But we can do also the opposite. So if we have a protein symbol grounding module, we can train only the DFA part by freezing the parameters of the symbol grounding and letting the other trainable. So in our experiments, we tried these two configurations. The configuration in which we learn the symbol grounding function is like so we are in a configuration in which the environment gives to the agent rewards and observation as usually, but it's also provide to the agent a high-level command, like this is the task, this is a specification of the task in a symbolic logical language. There is a language that the agent cannot comprehend at the beginning because it does not have the symbol grounding function, but what we see in the experiments is that it can leverage this knowledge to learn more efficiently the task to do. So the first experiments that we did was to test the capability of our framework to learn the symbol grounding function from an endlessly curated data set. So we created a data set of 40 episodes, 20 negative and 20 positive. So in 20 episodes, the agent cannot achieve the task. In the other 20, the agent can open the door and achieve the task. And we compare our framework with a baseline composed of a CNN plus an RNN on the same task of predicting rewards. And in blue and green, you can see the trained test accuracy of our framework that can reach high performances. In orange and red, there are the trained test accuracy of the RNN plus CNN model. As you can see, the deep learning approach really struggle to predict the rewards for this task because it cannot leverage the information of the DFA. So without this information, it's very difficult to predict the next reward. The other experiments that we did was to combine everything together with reinforcement learning. So we call these experiments online symbol grounding, in the sense that we are learning the policy and the symbol grounding function all together. So we have a reinforcement learning algorithm which uses actor critic, HUC, that is leading the interaction of the agent with the environment. While we interact with the environment, we collect all the experience and we create a data set. We use this data set to train the symbol grounding function, and then we use our estimation of the symbol grounding function to calculate the DFA state online. And the RL algorithm is run on the state composed of the DFA state and the environment state. As you can see, we tested our framework, we compared our framework with the baseline based on recurrent neural networks. So HUC run on a hidden state of an RNN. And the cumulative discounted rewards of the HUC plus RNN are shown in orange, while our framework is shown in blue. As you can see, our framework is able to outperform the baseline. That confirms our intuition that knowing the high-level specification of the task is useful for learning, even if this specification is ungrounded at the beginning. In the other two plots, we plot the classification accuracy over the nested word and the classification accuracy over the symbols in the image, and both can arrive to close to 100%. The other experiments that we performed was about DFA induction. So let's assume we have the symbol grounding module already pre-trained, and we want to learn the DFA from sequences of symbols and rewards. To do this, we train the part of the framework that is missing with cost entropy, but doing this, we do not exactly learn a deterministic final automaton. We learn a probabilistic final automaton, a PFA. And the transformation between PFA and DFA is obtained by using this softmax with temperature activation function. that work with the temperature. As close the temperature is as close the temperature is close to 0, and as the raw vectors of our matrix in the DFA becomes closer and closer to 1 hot. And so the PFA transforms into DFA. So we start by setting the temperature to a high value at the beginning and we decrease it during training. So at the end of the training, we can extract from the RNN part a DFA. We compared our DFA induction module to classical algorithm for DFA induction. That is Boolean, so it cannot it does not take as input probabilities, it only takes as input symbols, Boolean symbols. So we test the capability, the robustness of our framework to noise in the input symbols level. We did some experiments on the Tomita languages that are a common benchmark for DFA induction. And for each Tomita language, we corrupt the input symbols with some Gaussian noise with zero mean and different value for the variance. Here on the x-axis, you have the value of the variance. Increasing the variance of the noise, of course, both the two methods test accuracy decrease, but as you can see, our framework is more robust to noise in the symbol grounding. So concluding, we propose visual reward machines and Neural-Symbolic framework for reasoning and learning for non-Markovian, non-symbolic reinforcement learning tasks. And it is based on a probabilistic relaxation of both the symbol grounding and the temporal specification. And we've seen in the experiments that they can leverage prior information of the temporal property in order to outperform baseline. They cannot use this information. And they are more robust to noise with respect to DFA induction methods, combinatorial DFA induction methods. As future work, we would like to continue to investigate more this framework because it's very general. For example, we didn't experiment yet the DFA induction online, so DFA induction combined with reinforcement learning. And there are also other interesting directions. For example, it will be nice to see transfer learning. So if a visual reward machine can be transferred to another task or impose some partial knowledge on the DFA and others experiments that will have for future research. And that's it. Thank you for your attention.
Thank you very much. So we have time for questions. Are there any questions from the audience? All right, I do have a question, mostly a curiosity actually. Can you just say something more about that Minecraft data that you are using, just to understand, what are the different scenarios that are present in the data? You've shown an example. What is the variance of the episodes that can happen in this data?
Okay, in the data, so data are sequences of states, so are sequences of images in which we have the agent moving, so from one cell to another, and they are labeled with rewards, and the rewards is given by the DFA, that is. Here. So the reward is defined over the DFA state and is maximum on the final state because we want the sequences of symbols to be compliant with the DFA. For example, in practice we used as reward the distance of each state to the closest final state in the automaton. So to have a more dense reward.
Okay, thank you. Are there any other questions?
Thanks for the talk. So if you go actually to the slide right after this one, I think. No, okay, the one before. Sorry. Okay. So in the deep learning approach, you don't have these theoretical guarantees on the hidden state. And on the symbolic side, you do have them. And I missed it if you said this, but what about your approach? Do you have any guarantees, or you basically have the...
Okay, we have the same guarantees of reward machines if we are able to learn the right symbol grounding function or the right DFA. So in the limit we will have, yeah, just in the limit. Because right. it depends highly on your data and also on your knowledge. If your knowledge is too vague, is too general, you can have reasoning shortcuts, in the sense that you're not guaranteed to learn the right symbol grounding function if your LTLF formula is something too simple. For example, something that is like always negative or always positive, because it's trivially negative, trivially positive. Like the extreme examples, like if you have a contradiction or a tautology, they are not, but they're not guaranteed. They don't provide any feedback to learn the symbol grounding. But these are just extremes. In practice, you will have something that should be quite useful.
Mm-hmm. Thank you.
Thank you.
Other questions? Okay, so if it's not the case, we thank the speaker again. And I invite the next speaker to set up the machine. So, okay, the next paper is exploring mathematical conjecturing with large language models, and it's a work from Johnson and Smallbone, and the floor is yours, Mo.
Thank you. Yes, this paper is, I would say, an experience report in investigating the capabilities of GPT-4 as a lemma suggestion system. Of course, we now have to try ChatGPT for all sorts of tasks, and this is our experiment. So let me first say a little bit about conjecturing and automated lemma generation. This is something that I worked on for quite some time. So what you want to do here is, given some set of mathematical definitions and concepts, could be a functional program, for instance, like or something else. You want your system to automatically come up with some new interesting and non-trivial conjectures, which you can then go on to prove or do something else with. So this is a problem, of course, that people in AI have been addressing for a long time. I think the first system goes back to at least the 70s, was a system called AM, not AI, AM, based on heuristic search. So this was way into the era where symbolic AI was the thing. Later on, there's been systems like graffiti from the 80s, HR by Simon Colton, and MathSaid for algebra. And these systems, they were all based on heuristics and rules in various ways. There was no sort of data-driven learning. So I came into this field later on because I was interested at the time in automating proofs by mathematical induction. And these are not decidable, so you don't just give them to your automated prover and it comes up with an answer. But rather, you might quite often have to stop and go away and prove some auxiliary lemma, also by induction. So this can be quite tricky. But we developed some systems for doing that. One was called Isacosi, because it was, I don't know if any people here are familiar with the Isabelle Hall proof assistant. Some might be, hence the name. And then a later version of that system called Hipster. And these, in the background of Hipster, we had a system called QuickSpec. So this was something that was developed at Chalmers when I came there. Where we wanted to generate properties about functional programs written in Haskell. And it relies on automated testing. If you've heard of QuickCheck, which is a very famous automated testing tool for Haskell, it relies on that to generate its data. Okay, but these are the sort of symbolic side. More recently, there's been development into using more data-driven methods for automated conjecturing. So for instance, there is work by Joseph Urban's group in Prague that used GPT-2 to generate lemmas. They managed to do that with some success. Although it was very important to get the temperature exactly right, otherwise it started repeating the output or got the syntax wrong or repeating training data and things like that, but it was possible. Another example is done for the proof assistant Hall Light by Rabe. They use something called now I forget, but it's a tree-based neural networks. And they had some success, but around 10 to 30% of the conjectures were new and interesting. Otherwise, you got a lot of repetitions and alpha renamings of things that you had and stuff like that. So that's a problem with the neural models. They tend to give you a lot of stuff you already know. Another approach, which is by my PhD student, Solrun Einarsdottir, is to instead use slightly data-driven methods, but instead of trying to just train a neural network, you try to generate some templates or shapes that are common in lemmas. So we've done some pre-studies for formal libraries from Isabelle Hall, and we could see that there are some shapes of lemmas that are very common. So perhaps we should direct our symbolic systems towards these. Okay. Let me give you an example of what kind of things I'm talking about. So I think I can't look at my slides because then you can't hear me. But anyway, here is an example from one of these systems that I mentioned, Hipster, which is a theory exploration system for Isabelle Hall. So Isabelle Hall, for those of you who are not familiar, all you need to know is that it's a very popular theorem prover. Definitions are very similar to functional programs, so you can think of this as a functional program, what you see on the screen. And in addition, you have something called tactics, which are small kind of snippets that the theorem prover can execute, and by executing a sequence of tactic, it constructs a proof. Okay? So here we have something, it's insertion sort. In fact, this is one of my favorite examples. I got given this as an assignment when I was an undergraduate student, and we had to prove that indeed this insertion sort definition produced a sorted list. Very standard, but it was a bit difficult for me when I was an undergraduate. So later on, I set myself the task, okay, I want to automate this, coming up with the right lemmas, because you need some lemmas, and I want my tool to do that. That's something I want to do during my PhD. And I don't think I did it during my PhD, but a bit later, with this system Hipster. And here in this box, you can see what Hipster actually outputs when you ask it about these three functions. So it comes up there at the bottom. You can see actually what it repeats what we asked it, what we wanted to prove, and it uses something called lemma AA, which is that thing on the at the top, which is the sort of standard lemma you need to prove that the list is sorted. And you got a bonus lemma there in the middle as well. So that's how it works. And we have some generation of proofs here as well. So these proofs are all by induction and then some simplification. So they're quite standard proofs. Okay. So this was Hipster. This is purely symbolic. This is the kind of task that we're talking about. So now we have another system which is very popular by students trying to cheat on their homework, namely ChatGPT. So can ChatGPT generate lemmas like these? Zero shot. Is it capable of that? That's what me and Nick wanted to find out earlier this spring. So okay, so let's give ChatGPT the same input, so this little functional program about sorting, and let's see what it can do out of the box. So one nice thing is that when I put this in, it can give me a little summary, and it tells me what these functions do in natural language. That's kind of neat. Okay, let's move on. So now let's ask ChatGPT to give me some lemmas about lists, about these functions sorted, insert, and isort. And it says, sure. And it gives me a bunch of lemmas, and it gives me some proofs. Here it gives me, in one particular style, it's called ISAR. So those of you who are familiar with Isabel might know that there is this proof language that you can use, which is supposed to be a bit more human readable. If I run it again, though, I can get it in a slightly more brief way. So it's kind of depends where the probabilities takes us. So these screenshots are actually from when we started running it, which was GPT 3.5. While we were doing this, they released GPT-4, and that was better at coming up with proofs that were actually proofs. Because I don't know if you noticed, but there are a few steps here that, for instance, refers to lemmas that don't exist and things like that. But at least it gets sort of the idea that it should probably do some case splitting, it should probably do some sort of induction. So I'm not really expecting it to come up with completely exact proof, but it gives me a proof sketch at least, which is kind of nice. And then I can edit it a bit myself if I want to. And another thing which we noticed was that Isabel has these two styles of writing proofs, and once it starts going in one of the styles, it's consistent, so it continues that way, which makes sense because it's the most probable. People usually don't mix these two styles, but it was nice. Yeah, one of the things also that I want you to note is on the right-hand side, it starts talking about permutations, and I didn't ask it to do anything about permutations, but presumably in the training data, there's plenty of students who have gotten this as a homework assignment, and quite often they also ask you to prove it that it's a permutation. That's the other thing you need to prove that a sorting algorithm is correct. It sorts the thing and it doesn't inject loads of other stuff. So it suggests that I should also prove things about permutations there. Okay, so do we even need these symbolic theory exploration systems anymore? I mean, it's a lot of work programming them. They're difficult, heuristics and search and all sorts of things. Because, well, after all, hallucination is not a big deal. I can take this output, I can feed it into my Isabelle theorem prover, and it checks the results for me. And if it's something that it can come up with a counterexample with, then I just throw it away, and maybe I need to massage the proofs a little bit, but yeah, that's okay. But it's one problem here. Was that a good example? Of course not. As I said, this is going to have been seen many, many times in the training data. Way too many students have gotten this homework assignment. So how do we assess the capabilities on some truly novel tasks? List libraries, sortings are all over the internet. Also another thing that we noted is that Hipster, our system that I showed earlier, is of course on GitHub. What else do I have on GitHub? All my benchmarks and all my results, because I'm a good little scientist and I put my results up so people can read my papers and then go and check the results. And one of the things we noticed was that occasionally ChatGPT would spit out my benchmark results more or less verbatim. So yeah, definitely in the training data. So this is a bad example. So we had to try to come up with something new, or at least slightly newer, so something that wasn't, to our knowledge, formalized in Isabelle at least. So what we decided to do was to take an example that we had in Haskell. So this is not ideal, because that example was probably in the training data, but in Haskell. But we thought, okay, we'll try it anyway. We can come up with anything better. So this is a library by a guy called Henderson about functional geometry. So it describes combinators for pictures. So you can place them on top, beside, or next to each other. And what's a bit special about this library is that it draws the pictures when you compose them into a given bounding box. So you see that if you put two pictures of bunnies on top of each other, the bunnies kind of get squished to fit into this same square. And the same if you put them beside each other, they get squished. But this is nice. It means that these functions got some interesting properties, as we will see soon. This library, by the way, is quite famous. You can use it to create these MC Escher woodcut pictures. If you've seen them with patterns, that repeats themselves. Okay, so let's see what this drawing library. I know it's small. You're not supposed to see it all, but that's the sort of size of this drawing library expressed in Isabelle. So it's essentially a functional program. It defines a couple of types, including the type of drawing, and a bunch of functions which do the different operations on drawings. Here we could actually put all this stuff into the prompt, because by now we had GPT-4, bigger prompt size, great. We can pull the whole program in there. And what we asked it to do, well, here's the program. Now please generate some lemmas in Isabelle format about the functions blank, which is basically a transparent picture, over, putting two pictures on top of each other, beside, next to each other, rotate, flipping or mirroring, and rotating 45 degrees. So rotate rotates 90 degrees clockwise. Okay, remember now that these beside and above, they will split the bounding box and squish the image of the bunnies. So we keep that in mind. here's one sample run. I have another example. I have a poster tomorrow, so you can come and see more examples there. But what it is, so first of all, I should say that we also asked it to not produce any proofs in this case, because we wanted more lemmas. These are quite easy to prove, so we thought, okay, don't put any proofs, just put sorry. That's a keyword for I'm skipping the proof now in Isabel. So that was fine. But let's see. So first of all, it decides that blank, the transparent picture, is an identity element, which is, it isn't really, apart from over, this function here. So if you put a transparent picture on over another one, then you can see through it, and there's no change. So in that case, those two lemmas are correct. It does, however, think that blank is also an identity for above and beside, which isn't the case, because you remember it splits the bounding box. So this is not true. Furthermore, it thinks that all binary functions are associative, which they are not. It's only over that's associative, putting things on top of each other. So above and beside, they squish the picture, so they get squished in from different directions, essentially. So they're not true. But it very consistently thinks that binary functions are associative. It also thinks that binary functions should be commutative. In this case, it's only over that's commutative. The other two, they squish their inputs into another bounding box. So that's only true in one case here. Next, it believes that unary functions, we have two. So one is rotating and flipping. It believes that those sort of returns the same thing if you apply them twice, but that's only true about flip, not about rotating 90 degrees and not about rotating 45 degrees. Yeah. And then we get also some odd function here. Oh. We get some odd function here at the bottom about flipping 45 and rotating, which isn't true. Sorry, I flipped through all of this. Okay, so how did it do? To summarize, many conjectures, as you saw, were false. In fact, in this run, it was 10 out of 16 that were false. I mean, as I said, it's not a huge problem. I have my theorem prover. I have my counterexample checker in Isabel, so I can just very easily get rid of those things. So it's not a big deal. What's interesting to observe is that ChatGPT seems to have internalized some templates or some algebraic properties. So, for instance, it seems to very often assume that there should be some kind of identity element. In this case, it was this transparent drawing, blank. It thinks that binary functions ought to be associative and commutative. It's quite common. You see that in algebraic textbooks and loads of examples of it, presumably in its training data. Unary functions are their own identity, and binary functions distribute over each other. Sometimes it comes up with those things, but not always. Different runs, as I mentioned, gave different conjectures. So this was kind of a very templatey, so it comes up with these templates and not so much else. So if you come to the poster session tomorrow, you can see another example, which is a bit more locking in my poster. So how does this compare then? If we go back to these symbolic systems, was it time to throw out the symbolic systems? Well, maybe not quite. So if we compare it to QuickSpec, I'm sorry, I'm throwing loads of names of systems at you here, but QuickSpec and Hipster, they are basically part of each other, so they're very much integrated. But here, it's much more, of course, it's much more systematic and predictable what it will come up with. It will always figure out exactly which systems are commutative and associative And if they're not, then it will not include that. It will also come up with lemmas such as this one about over. So if you put any drawing over itself, then of course that's kind of an identity function. GPT-4 never came up with that at all because, well, it doesn't really know how this over function works. It's also a bit iffy about how functions distribute over each other, which symbolic systems will figure out. Very consistently, you will get things like if you rotate 90 degrees 4 times, you get the identity function. You only get that sometimes with GPT-4. And also more complicated lemmas, which are sort of more domain-specific, you will get with the symbolic systems, but not with the neural systems, such as the lemma there at the bottom, which is some sort of complicated way of putting things above and beside each other in a 2x2 grid, which is actually equivalent. So, on the downside, QuickSpec is a symbolic system. It does search, and it has a size limit. So here is a funny conjecture. If you rotate by 45 degrees 8 times, you get back to the original drawing. This ends up outside of QuickSpec or Hipster's size limits. It doesn't come up with that. Unless I increase it a lot, but then I will also increase the search space a lot, so that's not going to happen. Another question which is interesting is what happens if I have a bug in my definitions? So if I have a buggy program that I give to these tools. So ideally you would want some help and say, okay, you have a bug here. Here is a property that's not satisfied, that ought to be satisfied. But QuickSpec can't come up with such property. What happens if we have a bug in the program, which me and Nick has discovered many times over, is that you will have some property that's missing that you expect to see. And that's okay for us because we know what to expect, but maybe not so good if you're a programmer and you just see a bunch of properties. ChatGPT, on the other hand, it might still suggest the intended property, even though there is a bug and the property doesn't actually hold, because it looks like a property that ought to hold. So for instance, we had when we were doing this, we were in a hurry, we made a mistake in the rotate 45 function. So we would want, if you rotate 45 twice, that's the same as rotating 90 degrees. But QuickSpec didn't come up with that property. Okay, what was that? ChatGPT came up with it. Well, it turned out we made some subtle mistakes because we were in a hurry. There was a deadline to submit and all that. But ChatGPT kind of had enough data to jump to conclusion of what we were trying to write without us actually writing it. So it came up with this conjecture that was actually, strictly speaking, false, but it ought to be true. So that was a bit fun. So let's summarize a little bit. So what are the pros of using ChatGPT or some other big large language model as a theory exploration system? So names are informative. The symbolic system is blind to names. I could call my functions F, G, H. It wouldn't care. It wouldn't make a difference. For language models, it can sort of associate. So in the example I showed, it threw in permutation when I was talking about sorting, because those two functions are often together. We had some other example where it started talking about size, and sometimes that can maybe be a good little push for the user to say, okay, here's another function that you might want to include in your theory. Also, the neural system doesn't have restrictions on the shapes of lemmas, so inevitably the symbolic system will have some restrictions on size, for instance. It's much easier for it to generate equations than implications, so if you want complicated implications, that's more, the neural system has more freedom. It can come up with anything. What was quite nice is that it does seem to have this ability to suggest common patterns. So this is something that we might want to integrate with Solrun's work. Well, maybe we don't want a neural system to come up with dilemmas totally, but maybe it can give us some suggestions about good shapes that we can then explore symbolically. And another pro was this suggestion of correct properties even when I actually had a bug in the definition. Cons, I should wrap up quickly. It's difficult to do a fair evaluation. This was hidden behind a proprietary API. We don't know what's in the training data, so it might be cheating. It's a bit unpredictable. Could be a strength or a weakness, but different runs do give different results. If we want any sort of consistent results, then we need to run it many times and try to combine it. Hardware and energy consumption. We haven't talked about that very much in this conference, but let's face it, these quick spec and hipster system, they run happily on an old laptop, much older than this. It runs on my old laptop from 2014 or earlier. No problem, very quickly. And neural systems, no. I will have to use some cluster somewhere. So, yeah. Payment, of course, it's a commercial product. Does anyone want to pay to get conjectures? Probably not. So, yeah, I don't think GPT-4 as a theory exploration system is maybe a viable option. Some very quick final words. There are some interesting complementary features to purely symbolic systems, but it would be desirable to work maybe with some smaller transparent system, open source large language model. In this zero-shot setting, yes, we did get better results with a bigger model, of course, but and the context window can be a problem. Yeah, of course, we should try to do this with a smaller and carefully trained network. Here we're just going zero-shot. What can it do? If anyone interested in collaborating on these tasks, come and see me tomorrow. I have a poster. You can recognize it by, it's got bunnies and rotating and squished bunnies on top of each other. So look for the poster with the bunnies. Thank you.
Thank you. So are there any questions? Yes.
Thanks. So in actual mathematical use, lemmas are not just generated ad lib, but for a reason, right? And so I think this was clear in your first example. So the I-sort case. So I think the lemma there is what you would need to prove the step case in the induction, right? If I got it right. So you do the proof, you do the induction, you think, oh damn, now I need to prove the step case. I need this lemma, right? Mm-hmm. Whereas in all of the rest of your experiments, if I understood correctly, you're giving it the definitions of the functions, and then you just hope that interesting lemmas come out, yes, not informed by the dynamics of the proof. So question A, is that a correct understanding? And B, would you get more interesting lemmas if you introduce the dynamics of the proof as part of the lemma generation process?
Question A, yes, that's a correct interpretation. Okay. Question B, yeah, I mean, that's how I started way back when I was a PhD student. I was looking at these proof critics. So you went through the proof until you got stuck, and then you try to generate a lemma. Only problem is that it was just as hard trying to generate the right lemma from a point in the proof where you were stuck as it was for just taking these functions and saying, okay, just go bottom up and generate some interesting things. So when I actually, at that point at least, I didn't manage to get any more interesting lemmas from being inside a proof than I got from just doing it bottom up.
But there are infinite number of boring lemmas.
Yes.
You come from Emra, right? It was at some point an enterprise you could buy your
I might have been involved in that. Yes. Yeah. So well, yeah. Well, there is. I didn't have time to go into it, but in our symbolic systems, there are actually plenty of heuristics to stop it generating boring lemmas. So, like for instance, one of the things also in theory mind that you mentioned is that we have heuristics that make sure that you don't generate things that are, for instance, more complicated instances of some lemma that you already know. We throw away lemmas that are trivial to prove. So, for instance, hipster that I mentioned, you can configure it so if it needs to use some more complicated reasoning, such as induction, it judges it as being more interesting than if it's something you can just do by simplification.
But you're not so optimistic about using the dynamics of the proof as a source?
I mean, that sounds like the obvious things to do, but so far I haven't gotten it to work. Maybe you can do it and you can narrow it down so you only get the specific lemma. This is where I started. But so far in my experience, that was no easier than trying to just do it bottom up and then you get some extra lemmas as a bonus. Yeah, thanks.
Okay, just a very quick question.
So maybe you explained it and I missed it. How do you ensure that it's a well-formed formula that that ChatGPT puts out?
So I make no such guarantees.
Okay.
It just happens that it seems to have seen enough Isabelle code to produce well-formed formulas, which was very nice for me because you could also go from Isabelle doing these different proof styles, for instance. I don't have to write pretty printers and parsers. I've done plenty of that. So it seems to be very good at actually getting the syntax right, which is very nice.
Indeed,
but I think that is the size of the language model.
Thanks.
So let's thank the speaker again.